diagram of the underfloor heating job that I've done. Someone commented on the other video and asked for a pipe schematic because I couldn't really see it. So I've drawn it out and I'll try and explain it the best I can. So what I've done is I've created a primary loop down here, which is just my flow and return joined together from the boiler, and I did that in 28mm pipe. The reason I increased the pipe size was just to give it a little bit more volume on my primary loop. So that's my primary. Off that, we've got some closely spaced T's, closely coupled T's, or CCTs. And those are specifically spaced T's in a position of, on the flow going into it, it's a minimum of 4 times D. D is the diameter of the pipe that you're using. So from that point there, from that T to your elbow, your first elbow, you need a minimum of 4 times D, which is 112mm. So straight out my boiler, from there, I need a minimum of 112mm before a bend. Then the distance in between the T's, same again, sorry, maximum of 4 times D, so it can be no more than 112. So realistically, just a little gap in between your T's there, that will do it. And then on the return side of those, it's a maximum of 8 times D. Sorry, a minimum of 8 times D. And that's how you space those there. So they could have been there, they could have been there, they could have been anywhere, as long as I got that spacing kind of as it should be. I put them there just as a pipe layout and how I could get it out. So as we come off there, we've got our flow pipe, which comes along, and that tees down there to my underfloor heating circuit, and then across here to my radiator circuit, and then we've got the radiator pump and zone valve there. And that goes off to our radiator circuit. So our flow comes down here through the zone valve into the mixing valve, and then that will give us a blended water temperature as it mixes with the return water, and that will go down to our underfloor heating circuit. Return pipe, same again, so that returns back from the radiator circuit. I've put a non-return valve there just in case there's any risk of reverse flow down that return circuit. The resistance is going to be much greater inside the underfloor heating circuit, so I'm not too concerned about it pushing back that way. It wouldn't hurt it too much anyway, obviously, because slabs take ages to warm up. Also put a non-return valve there, and I've teed my underfloor heating circuit in after, so it will reduce the flow pipe return temperature, sorry, reduce the return temperature possibly a little bit further. So that's how mine is piped up. I'm not sure what some of you understand. I mean, my forte is repairing boilers. I'm not an installer, that is not my forte. However, I have to repair stuff that's fitted like this or fitted like that. So this is why I learn stuff like this, or why I've gained the knowledge of wanting to do it. I am getting install jobs from knowing stuff like this and being able to resolve the issues and correcting it. So I think the way heating systems are changing, if you're a breakdown engineer, I think you're going to need to know stuff like this and how systems work and why it doesn't warm up and how you're going to resolve it. So Andrew Millward, Adam Chapman, they do loads of videos on this sort of stuff. I'd advise and recommend following these guys. So a little explanation. So the distance between my close couple T's there is 112mm. Close couple T's, really the pressure loss in between those is that minimal that you can run different circuits, hydraulic circuits off that without causing impact on one another. The reason why you're going to use close couple T's or a low loss header there, so kind of the difference between a low loss header and close couple T's is A low loss header will slow the velocity of the water down to about 3 meters per second, which will allow dirt separation. Close couple T's don't do that, so you're still aiming for about 1 meter per second in your central heating pipes as an optimum. So it can range really from 0.5 meters per second to 1.5 meters per second. So that's how I did my system. Just some other little bits I'll touch on while I'm doing the video. So how this basically works is that pump inside the boiler runs this primary loop here, and it'll just circulate there and look after itself. So that should maintain, realistically, you're looking for a DT of 20 degrees. DT means the difference between the flow and the return. So all heating systems nowadays, they're designed for a DT of 20 degrees, which will change. It is going to change. Some are designing for a DT of 15 at the minute. So that will maintain that flow there. You may need to fit a gate valve to slow it down to obtain the 20 degrees, or a flow setter, or with a modulating pump, it may modulate and just do its own thing and take care of that. And then off that, we've got our central heating pump, which will run the radiator circuit. And then we've got the underfloor heating pump. And the reason we've done hydraulic separation is what will happen is radiator circuit is running at a different flow rate and DT to the underfloor heating circuit. What will happen is when you put your radiator circuit on and you put your underfloor heating circuit on, without the close couple T's, it will draw the heat away from the radiator circuit, and you'll get complaints of radiators just not warming up properly. So a little quick way of working out your flow rates is you've got the kilowatt. Let's say we've got a heat load of 6 kilowatts for our radiators. We take our 6 kilowatts and we're going to divide that by 4.2, which is the specific heat capacity of water, and 20 degrees C, which is our DT. And we times them together first and then divide 6 by that, which will give us an answer of 0.071 litres per second. We want litres per minute, so we'll change times that by 60, which will give us 4.28 litres per minute. If we follow the same formula for the underfloor heating, these are just for illustration. For example, 3 kilowatt heat load on one of these circuits here, times the DT of 7, because underfloor heating should run at a DT of either 5 to 7. So we're going to use 7 times 4.2. First, 3 divided by that sum gives us 0.102 litres per second, times by 60 is litres per minute. So you can see straight away we've got 2 different flow rates there, different pressure losses across it. So therefore, if we set it up like this, we can balance each system and circuit accordingly. Just going down here to these underfloor heating circuits, you'll come across different patterns. These are probably your most common ones that you're going to see. This pattern here, I can't remember the actual name of it now, bifilar or something like that, I think it is. This gives out, this is the most efficient way of doing it, obviously, because as your heat comes down, it transfers. A better way of doing it in larger circles are going round a bigger area, so it loses its heat on the return, coming back out of its spiral. If you was to run it this way, it will lose its heat across the side that it's travelling across, so it just doesn't heat up just as good. As I mentioned in the video, you want to really aim for 100 centres. So 100 centres is between that pipe there and that pipe there. The more pipe you can put in the ground, the more heat you're going to get out the ground, and the lower you can run your flow temperature out of the boiler. And this goes the same really for radiators. The bigger the radiator, the lower you can turn your radiator temperatures down, you flow down from the boiler and save energy. And this is what it's all about at the minute. Heating systems are changing. Like I said, my forte is repairing stuff, but you know, this is not my forte doing this sort of stuff. I highly recommend, if you want to learn stuff like this, you go on one of these courses. Kimbo Betty's course, Rob Berridge, and then before you even get onto the Heatgeek course, get these two out of the way first. So it'll help you massively to resolve heating problems, system design problems and stuff like that. So yeah, why you would fit close couple T's is if you want to run multiple zones at different flow rates, at different DTs, or if your pump is not actually up to the job of circulating around the system. So the first time I ever used close couple T's was probably about 6-7 years ago. I had a job. This is how I drew it out at the time. Looking back now, there we go. I went round all the radiators, worked out what I'd got, heat requirements from the radiators, which was 23 kilowatts. And at the time, I'd got a 40 CDI green style boiler. So a lot of people look at that and think, well, I've got 40 kilowatts, I've got 23 kilowatts demand, why is it not working? And this is kind of a schematic of what was happening for me. So all these radiators over here in an annex, we've got 1, 2, 3, 4, 5, 6 radiators. I couldn't get them to heat up. Even with all these turned off, I still could not get these radiators to warm up. So, and the reason why I couldn't get it to warm up was because the negative head loss on the pump and what was required from my system, my pump just wasn't up to doing it. So what I've noticed a lot of installers make the mistake of is this: they just think 30.9 kilowatt, it will do the system easy. It's not actually about that, it's about how much water you can transfer down these pipes to get that heat requirement there. So as the heat exchanger becomes bigger inside a boiler, it becomes deeper and it adds a greater restriction to the pump. So this is where you need to start understanding pump curves and working out pressure losses across pipe work. So I think if I remember rightly, I've lost the actual chart. I literally sat down and went through every part, worked out how many kilowatts was required, pipe work, pipe runs, and from that I generated the pipe loss, pressure loss across my system. When I worked out the pressure loss that I was losing across here, and then I added that to the boiler pressure loss, that exceeded what the pump could actually give me. So therefore I created some close couple T's below the boiler. Same again as I did with this one. The pump looks after my primary loop, and then my secondary pump fed this zone, and I ran another flow to feed this zone around here, and another return coming back, I think, joined in, and then these work perfect. 10 other installers had been to this job before me and couldn't resolve the issue, and this was the first time I have used close couple T's 6-7 years ago, and they've got me out of trouble so many times. One of the things with central heating is you will always evolve, you will always learn things, you know. Don't be afraid to fit something and then it doesn't work. You know, obviously there's the cost implications to everything, but close couple T's are a good one. You're talking the price of 2 T's, 2 22mm T's or 2 28mm T's, and just learn, work out, and you know, you'll find stuff about it. One thing I learned when I went on Kimbo Betty's course was, what he said to me was, you can seriously fit something wrong, but it will work in a fashion. It might not work efficiently, but you will always learn from your mistakes. So that's my little explanation on close couple T's on this system. Just so you don't get confused. So how I've put my close couple T's there, I've created a primary loop and I've come off that, and both my circuits come off the secondary loop. Andrew Millwood and Adam Chapman have done numerous videos, so I would advise you going to their channel, subscribing to those. Heatgeek, also Kimbo Betty and Rob Berridge, Heat Engineering, Heating Academy. those guys. And this is like serious, that's a serious course, trust me. So a little sketch on what Andrew and Adam are constantly on about is, what you see is people create a primary loop there and they run the radiator circuit off the primary loop, and then they run the underfloor heating circuit off. Some close couple T's there. Those are not actually close couple T's the way it's been done. You're creating a bypass, and what will happen is water will always take the route of least resistance. So when this zone valve, there's going to be a zone valve there, let's just draw it in. When that zone valve closes, the water's going to use this as a bypass, and it's going to bypass along there. You are going to get some heat go up the radiator circuit, but not much, because water will take the route of least resistance. So it's going to circulate around this loop here and go back to the boiler, and you're going to have problems there. So this is the why you do it the way you do, or the way it's tried and tested. You create a primary loop and everything comes off your secondary. So like I said, get on to Andrew Millward, Kimbo Betty, Rob Berridge, Adam Chapman. If you want to learn about hydraulic separation, future heat systems and stuff like that, those are the courses you need to be going on. The other thing is, if you can design a system, or you understand how to design a system for lower flow temperatures, which is part of the new Part L regs that are coming in, if you can get a property to run on low temperature now, as it is, and all the DTs and everything match up and it's all okay, then you're kind of proving that that house is set to run on a heat pump. Because if you can run at the same temperature, it doesn't matter what the heat source is. So that's my little video on that. Hope that helps some of you.